We have another problem in manometry, and this will be helpful in helping you to prepare yourself for the exam, which involve manometry problems. So as you can see here, you have a YouTube manometer, and then it's having two fluids. The first is water, which is the greenish part, and the unknown fluid, which is the gray part. So what this problem asks you to find is the value of the specific weight or gamma of this unknown fluid, and you are informed that you need to express your answer in SI. Now, the first thing that we know, and I think you already know this based from our task, is that we need to set um, points with which where we will start our measurement. Now, in my case, uh, I will be labeling this point here. I will call this my point A, and this level here my point B. And as I've mentioned in class, you have the freedom to either start in either point. So you start in A or B, it doesn't matter. As long as you are um, concerned and you always think that whenever you go down, the pressure increases. So that means that the sign of the pressure is positive. But for my case, I will be starting from point A. So when I start from point A, I will have this expression here. I will have the pressure at A, and then since I will be going down up until this point here, I will have that as plus increase in pressure since that is going down, rho of what fluid that is still in water. So the density of water, G on Earth, we don't have a problem with that. And I will label H1. So take note that my H1 is just from the top up until the interface of the water and the unknown fluid. That is my H1. Okay, now the next thing that I could do is actually I could take the raw GH of this fluid, but take note I will add a pressure from that point up until the bottom. But when I do it on the opposite side, what I mean is in this part, I will also subtract the same amount of pressure that I added, okay, in this level. That is why I will skip. So this is the point where I will skip this part and jump instead on this water level, on this fluid level. So when I do that, I will go up from this point up until the top portion. I will label this as my height 2. I will call that as height 2. So I will have then, since I'm going up, I will have decrease in pressure, so minus the density of sub U, meaning the unknown fluid, the G, and then height 2. Okay, height 2. And then from this interface of the unknown fluid and up until up until the top portion in the line of B, I will still have a decrease in pressure since I'm going up. So I have minus, or I will subtract the density, or what fluid am I moving in this case? I am now moving in water, so minus the density of water, G, and I will denote from this level up until point B, I will denote that as my H3. My H3 there, and that is equal to, I will equate that to the pressure at this point in the very most top, or the topmost level, which corresponds to point B, or the pressure at point B. Okay, so I have set up my governing equation for this problem, which is the one that I shaded from the top. Now recall from the problem that you're asked to find for this value, the specific weight or the gamma, and that is just specifically the specific weight of the unknown fluid U, or specific weight that is just the density of U multiplied by the acceleration due to gravity. So from the equation above, I will try to simplify this one such that I will have an expression for the specific weight of U. Okay, when I do that, I will continue in this portion. When I do that, I have PA plus the density of water, H2O, okay, and G, and then H1. So let us try to neglect first the whatever the values of H1. Let's try to set up the equation first. And then take note that my gamma U, or specific weight of the unknown fluid, is this term here. Thus, I will simplify that to be gamma U, that density rho sub U and G, that is just gamma U, and then H2 minus the density of water, and then you multiply it by G H3, and that is equal to PB, right? The next step that I am going to do in this case is I want to have an expression where this term gamma U is isolated. It means I will transpose this to the opposite side of the equation. At the same time, this P sub B will be transported or transposed to this portion, the opposite side of the equation. And when I do that, I'll have a simpler looking equation, which will be P sub A, and I will take into account PB that I transpose here. So I'll have minus P sub B, since originally it is positive and it crosses here, so it must be negative. And then I will take into account this term plus the density of water, okay, G H1, and then this term will be thrown to the opposite side of the equation. So that means I'm going to proceed with this one minus the density of H2O. It's not working, H2O. And then multiplied by G H3. And then when I do that, this term which has a negative sign will be positive, and it will be on the right hand side now, H2. Okay, now you might be saying that the most sensible thing to do, although this is still valid, is to multiply both sides by H2 such that the only remaining term will be the gamma U. But I will refrain from doing that because I could further simplify this term here. So let me just simplify this. I have PA minus PB, and then these two terms, which I underline, could be further simplified since there is a common term of gamma H2O, rho H2O, and the acceleration due to gravity G. Therefore, when I factor these two terms, this term from these two terms here, what will remain is just H1 minus H3. So I'm hoping you can follow why that happened. And that is equal to gamma U H2. But wait, before dividing both sides by H2, you need to note that the pressure at A, I think I will point it in yellow, the pressure at this point and this point actually has the same value because PA is just equal to the atmospheric pressure, since that is open or exposed to the air outside. The same case happened with PB. That is also open. It's noted in the illustration that that is open and exposed to the air outside. Therefore, the pressure at point A and point B are just equal, and it is equal to the atmospheric pressure. Therefore, their difference will be logically be zero, since they have the same value. PA 1 ATM minus 1 ATM, that will be zero. Therefore, you have now reduced your equation to a simpler looking equation such as this one. Okay, so you have now the density of water, H2O, G, and then the difference of height of H1 minus H3. But at this point, we don't know what the values of H1 and H3 are. And then gamma U, H2. So yes, we have simplified our equation. But to do further simplification such that we can isolate gamma U, because that is what we want, we multiply both sides by 1 over H2. And when you do that, H2 will cancel out on the right hand side, leaving gamma U behind, which is what we desire. So we have now the density of water, G, the difference of H1 minus H3, H1 minus H3, and that is divided by H2. H2. And what is left on the right hand side is gamma U. Okay, now the next thing that we need to do, okay, let's find for the specific values of H1. So all you are going to do is to analyze the geometry of the problem and note that H1 is just from the top up until this point here, which is the interface of your water and the unknown fluid. So that means that H1 will just be the entire length from bottom to top, which is 5.5, and then you subtract 1.4 inches from it. 1.4 inches. And when you do that, you'll have H1 is equal to 4.1 inches. Okay, so that is the value of H1. For H2, the same thing. You have to analyze the geometry of this problem and take note that H2 is just from this level, which is 1.4 from the bottom, start here, up until this point, that is your H2. Therefore, to do that, you get the height, 3.3 inches, from the topmost portion to the bottom, and then you subtract the height from the lower portion to the bottom, which is 1.4 inches. And that will give you H2 equal to 3.3 minus 1.4. That will give you a value of 1.9 inches. So let me just check 5.5 minus 1.4. Yep, it's 4.1. And we are sure of these two values of height. And for H3, so try to look into the problem. H3 is from this boundary of water and the unknown fluid up until the top. And to get that, the same thing. You get the entire height of 4.9 inches. And then you subtract from the bottom up until the lower level, which is 3.3 inches. And that will give you the value of H3 to be equal to 4.9 minus 3.3. That will give you a value of 1.6 inches. Alright, so at this point we have solved for the specific values of height. Now this is where the students will probably do the extra mile, which is not necessary, by actually converting inches to meters, since the problem dictates to have it in SI. But you will see later, if you are clever, that you don't really have to do that, because it will just cancel itself out from the solution. So to show you what I'm talking about, let's plug in the values here. So we have gamma u, and that is just equal to the density of water, which is 1,000 kilograms per cubic meters. So you assume this value whenever the density of water is not given at a specific temperature, automatic, that one. And you have 9.8 meters per second squared, and then the difference of H1. H1 is 4.1 inches. The difference of H1 and H3 is 1.6 inches. And everything is divided by H2, which is 1.9 inches. So when you do that, you will get gamma u. So the first two term here, this one, 9.8 times 1,000, you'll have 9,800. For the units, okay, you don't have a problem with kilogram, copy that. Meters divided by m cubed, so that will be per meter squared second squared. And then 4.1 minus 1.6 is just equal to 2.5. So you have 2.5 inches, and then you divide everything by 1.9 inches. So this is what I am talking earlier. So you don't have to convert that inches to meters, because inches will just cancel out. Okay, so you have to be clever in terms of doing conversions, whether conversion is necessary or not. So you work with that on your calculator. I'm just plugging in the value, 9,800 times 2.5 is divided by 1.9, and I get 12,894.74. The unit is in kilogram per meter squared second squared. But this kilogram per square meter second squared is just Newton per cubic meters. So this is something that you are going to show it yourself. So this is then the gamma u, or the specific weight of the unknown fluid. So we have solved that just by looking at how it arranges itself based on the heights. So 12,894.74. So let's check whether we arrive with the same result. So it's 12,895, which is just the rounded off value of what we get. So that is how you solve this manometry problem.